am Priya from BSc Chemistry Honors first year. Today I am making a video on thermodynamics. Introduction. The chemical reactions are invariable accompanied by energy changes which ordinarily appear in the form of evolution or absorption of heat. Thermodynamics is the branch of physical chemistry which deals with the thermal or heat change caused by chemical reactions. The energy change that occurs in a reaction is largely due to change of bond energy, change of potential energy that results from the breaking of bonds in reactants and formation of new bonds in product. We have studied in unit 11 that every substance has a definite amount of energy known as intrinsic or internal energy. Its exact value cannot be determined, but the change in internal energy delta E can be accurately measured experimentally. Factors affecting heat of reaction. There are some factors which affect the quantity of heat evolved or absorbed during a physical reaction or chemical transformation. These factors are: first, at constant pressure or at constant volume; second, physical state of reactants and products; third, amount of reactants and products; fourth, temperature; fifth, pressure. The physical states in a thermochemical reaction are represented by the symbols S, I, G and aqueous for solid, liquid, gas and aqueous states respectively. Consider a reaction. This reaction indicates that which 1 mole of hydrogen reacts with 0.5 mole of oxygen, 1 mole of water is formed and 68.32 kilocalorie of heat is evolved at constant pressure. If 2 mole of hydrogen are burnt, the heat evolved would be 2 into 68.32 kilocalorie. This equation is not complete thermochemical equation because it does not specify water is in the form of steam or liquid. There is difference in the value of hydrogen if water is in the liquid or gaseous state as given below. Enthalpy of reaction or heat of reaction. The heat of reaction is simply the amount of heat absorbed or evolved in the reaction. As we know that amount of heat absorbed or evolved at constant temperature and pressure is called enthalpy. Hence, the amount of heat change during a reaction at when internal energy of reactants is greater internal energy of products. The difference in internal energy delta E is released as heat energy. Delta E is equal to E products minus E reactants. Such as reaction is called exothermic reaction. If the internal energy of the products is greater than internal energy of reactants, heat is absorbed from the surroundings. Such as reaction is called endothermic reaction. The amount of heat released or absorbed in a reaction is called heat of reaction. As we have discussed above, the energy change in chemical reaction are largely due to breaking of existing bonds between the atoms and formation of new bonds. Thus, thermochemistry produces useful information regarding bond energies. Heat of reaction. Thermochemical reactions are studied either at a constant volume or at constant pressure. The magnitude of change observed under the two conditions is different. The change in internal energy delta E is the heat change accompanying a chemical reaction at constant volume because no external work is performed, but at constant pressure there is change in internal energy and work is also evolved because of expansion or contraction. In the laboratory, most of chemical reactions are carried out at constant pressure, atmospheric pressure, rather than at constant volume. In order to study heat changes for reactions taking place at constant pressure and constant temperature, a new term enthalpy have been introduced. As we have studied in Unit 11, the enthalpy of a system is defined as the sum of internal energy and the product of its volume with pressure, that is, H is equal to E plus PV, where H is enthalpy, E is internal energy, P is the pressure, V is the volume of the system, and the term H is also called heat Heat content, like internal energy, enthalpy is also a state function and it is not possible to measure its absolute value. However, a change in enthalpy delta H accompanying a process can be measured accurately and is given by the expression delta E is equal to H products minus H reactants. In these cases, however, delta HP and delta HR, i.e. QP and QR, would be equal as there is no volume change involved. Now we take the following equation. C7H8 plus 9O2 is equal to 7CO2 plus H2O. In this case, QP is equal to minus 930 kilocalories and QR is equal to minus 928.8 kilocalorie. Relation between enthalpy of reaction at constant volume and at constant pressure. The quantities delta H and delta E are related to each other by expression from equation 12.1. Delta H is equal to delta E plus P delta V, where delta V is the change in volume that takes place in a given reaction. Since QR is equal to delta E and QP is equal to delta H, then QP is equal to QR plus P delta V. For n moles of an ideal equation of gas, PV is equal to nRT. Suppose N1 and N2 represent the number of moles of gaseous reactants and gaseous products respectively, and suppose N2 is greater than N1, then increase in number of gaseous moles is equal to N2 minus N1 is equal to delta Ng. Then P delta V is equal to PV upon N. Delta Ng is equal to RT into delta N. As PV is equal to nRT, then P delta V is equal to delta Ng RT. Let us discuss, for example, dissociation of ammonia into nitrogen and hydrogen in the reaction involving combination of hydrogen and nitrogen. At constant pressure and temperature, the change in enthalpy delta H will be equal to change in internal energy delta E and the work done in expansion or contraction P delta V. Hence, delta H is equal to delta E plus P delta V. Therefore, while heat change in a process is equal to its change in internal energy delta E at constant volume, it gives at constant pressure the enthalpy change delta H. Delta E is equal to heat change at constant volume, delta H is heat change at constant pressure. For reaction involving solid and liquids only, the change in volume delta V is very small and hence the term P into delta V is so small then it is neglected. For such reaction, delta E is equal to delta H. In case of gases, we have to simplify the reaction is taking place at constant pressure or at a constant volume. Because the volume of P into delta V is appreciable, most of such reactions are however studied at constant pressure and change in enthalpy delta H is involved. Exothermic and endothermic reactions. Reactions that gives out heat which are accompanied by evolution of heat are called an exothermic reaction. On the other hand, reactions which are accompanied by the absorption of heat are called endothermic reactions. Let us consider a general reaction at constant pressure. A plus B is equal to C plus D. Suppose enthalpy of A is HA, enthalpy of B is HB, enthalpy of C is HC and enthalpy of D is HD. Then heat of reaction at constant pressure delta H is equal to difference in enthalpy of products and the reactants. Delta H is equal to delta H products minus H reactants. The value of heat of reaction delta H may be 0, negative or positive. When delta H is equal to 0, the enthalpy of reactants and products become the same. No heat is evolved or absorbed. In case of delta H is negative, the sum of enthalpies of the product is less than the reactants and difference in enthalpy is given out in the form of heat. Such reactions in which evolution of heat energy takes place are called exothermic reactions. Similarly, heat of reaction at constant pressure is given by the relation delta H is equal to H2 minus H1, where H2 as H1 are heat content or enthalpy of products and reactants. The reactions 12.3, 12.4, 12.6 and 12.7 were first derived by Kirchhoff and are called Kirchhoff's equation. These equations are used to calculate heat of reaction at a given temperature provided heat of reaction at some other temperature and when the heat capacities of product and reactants are known. Different type of heat of reaction, enthalpy of reaction. Heat of formation, the change in enthalpy that takes place when 1 mole of the compound is formed from its elements is known as heat of formation. It is denoted by delta H. For example, the heat of formation of ferrous oxide may be expressed as constant pressure and temperature may also be called enthalpy change. Heat of reaction may be defined as the amount of heat absorbed or evolved in a reaction when number of moles of reactants as represented by the balanced chemical equation change completely into the products. It is very important to be noted that heat of reaction varies with change in temperature. Hence, we must mention the temperature at which the reaction is taking place. It is also convenient for comparison to fix up some temperature as standard or reference. By thermodynamic convention, the state of substance at 298 Kelvin and 1 atmosphere pressure is taken as its standard state. The heat change accompanying a reaction taking place at 298 Kelvin and 1 atmosphere pressure is called the standard heat change or standard enthalpy change. It is denoted by delta H naught, variation of heat of reaction with the temperature. The heat of reaction changes with the change in temperature of a gas due to variation in its specific heat. The equation representing the variation of heat change of reaction with temperature is known as Kirchhoff's equation. At constant volume, the heat of reaction delta E is given by the relation delta E is equal to E2 minus E1, where E2 is internal energy of product and E1 is internal energy of reactants. Differentiating this equation with respect to temperature, keep volume constant. Then we get given below. Here CV into 2 is the heat capacity of product and CV into 1 is heat capacity of reactant. On integrating the above equation between the limits T1 and T2 and keep in view that when temperature is T1, heat of reaction is delta E1. When temperature is T2, then heat of reaction is delta E2. Is taken as minus 13.7 kilocalorie. The enthalpy of dissociation of acetic acid may be taken as 0.5 kilocalorie. The heat of dissociation of a weak acid or weak base may be defined as the change in enthalpy of the system which 1 mole of it is dissociation into ions. Some other definitions. Heat of fusion. Heat of fusion is defined as heat change or enthalpy change when 1 mole of solid substance is converted into liquid state as its melting point. Here ice melt at 273 Kelvin and change into liquid water by absorbing 1.43 kilocalorie heat. It is found that greater the heat of fusion of substance, higher the magnitude of intermolecular forces. Heat of vaporization. The heat of vaporization is defined as change in enthalpy when 1 mole of liquid is converted into vapor or gaseous state as its boiling point. For example, 1 mole of water is converted into steam at 100 degrees Celsius or 373 Kelvin. The heat absorbed is 9.71 kilocalorie, which is heat of vaporization of water. Heat of sublimation. In sublimation process, a solid changes directly into gaseous state without changing into liquid state. Sublimation occurs at a temperature below the melting point of solid. Heat of sublimation is defined as the enthalpy change when 1 mole of solid is directly converted into gaseous state at a temperature below its melting point. For example, the heat of sublimation of iodine is 14.92 kilocalorie per mole. It can be represented as Fe plus S is equal to Fes. Delta H is equal to minus 24.0 kilocalorie. The equation can be explained as 1 mole of ferrous reacts with 1 mole of sulfur to form 1 mole of ferrous sulfide in solid form, and 24 kilocalorie heat is evolved. The reaction between gaseous hydrogen and gaseous chlorine to form gaseous hydrogen chloride. It is represented by the equation H2 plus Cl2 is equal to 2HCl. Delta H is equal to minus 44 kilocalorie. This equation means 1 mole of gaseous hydrogen reacts until 1 mole of gaseous chloride to form 2 mole of gaseous hydrogen chloride, and 44 kilocalorie heat is evolved. It may be noted in this case that 44 kilocalorie is not heat of formation of HCl, because this amount of heat is evolved when 2 moles of hydrogen chloride are formed. The heat of formation of hydrogen chloride would be minus 44 by 2 is equal to minus 22 kilocalorie, and the equation can be written as half H2 plus half Cl2 is equal to HCl. Delta H is equal to minus 22 kilocalorie. Standard heat of formation. The standard heat of formation delta H naught is the enthalpy change when 1 mole of substance is formed from its elements in their standard states. This is all substances are at 298 Kelvin and 1 atmosphere pressure. Delta H naught values may be exothermic or endothermic. Determination of enthalpy of reaction. Enthalpy of reaction at 25 degrees Celsius, 298 Kelvin can be determined if delta H naught of reactants and products involved in the reaction are known as delta H naught is equal to delta H naught products minus delta H naught reactants. Similarly, heat of reaction at constant pressure is given by the relation H delta H is equal to H2 minus H1, where H2 as H1 are heat content or enthalpy of products and reactants respectively. Differentiating equation 12.5 with respect to temperature at constant pressure. Here Cp into 2 and Cp into 1 are heat capacity of product and reactants respectively, or D into delta H is equal to delta Cp dt. Integrating the equation between temperature T1 and T2, we have given below the relations 12.3, 12.4, 12.6, 12.7 were first derived by Kirchhoff's and are called Kirchhoff's reaction. These reactions are used to calculate the heat of a reaction at a given temperature, provided heat of reaction at some other temperature, and when the heat capacity of products and reactants are known. 12.8 Different types of heat of reaction. Enthalpy of reaction. Heat of formation. The change in enthalpy that takes place when 1 mole of the compound is formed from its elements is known as heat of formation. It is denoted by delta HF. For example, the heat of formation of ferrous oxide may be expressed as the heat of solution of an electrolyte may be due to energy change involved during ionization or some hydrate formation, as in sulfuric acid. Usually heat is absorbed when ions are torn apart from each other in the process of solution, and heat is evolved during hydrate formation. Heat of neutralization. The change in heat content enthalpy of the system which when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of base, or vice versa, in dilute solution is known as heat of neutralization. Following are some examples of heat of neutralization. From these equations written above, it is observed that heat of neutralization of a strong acid and strong base is minus 13.7 kilocalorie. This can be explained with the help of the theory of ionization. If Ha and BOH represent any strong acid and strong base respectively, and equivalent amount of these in dilute solution be mixed, we have H positive aqueous plus A aqueous plus B aqueous plus OH aqueous is give to A aqueous plus B aqueous plus H2O. Delta H is equal to minus 13.7 kilocalorie. Hence, H positive aqueous plus OH aqueous is equal to H2O. Delta H is equal to minus 13.7 kilocalorie. Thus, the heat of neutralization of an acid and a base is merely heat of formation of water from hydrogen and hydroxyl ions. If, however, the acid or alkali is weak, the enthalpy of neutralization is different because the reaction now involves dissociation of weak acid or weak alkali, or the neutralization of acetic acid with sodium hydroxide, for example, involves the dissociation of the acid as well as the usual neutralization of H positive and OH negative ions are represented below. CS3 COOH, CS3 COO negative plus H positive, H plus aqueous plus OH aqueous is equal to H2O. As H ions are neutralized by OH negative furnished by the completely dissociated sodium hydroxide, more H positive ions are formed by the dissociation of acetic acid to re-establish the equilibrium. Thus, both the reactions proceed side by side till acetic acid is completely neutralized. The enthalpy of neutralization of acetic acid by sodium hydroxide has been found to be minus 13.2 kilocalories, since the average value for the combination of H positive and OH negative ions. Heat of transition. The change in enthalpy when 1 mole of an element change from one allotropic form to another is known as heat of transition. For example, transition of a diamond into amorphous carbon be represented as Hess law of constant heat summation. The energy change accompanying chemical processes are governed by a general principle known as Hess's law. This law states that the amount of heat involved or absorbed in a process is the same whether the process takes place in two or more different ways, in one step or in several steps. Let us suppose that a substance A can be changed to Z directly. A is equal to Z plus Q1. Delta H is equal to minus Q1, where Q1 is the heat involved in the direct change when the same change is brought about in stages. A is equal to B plus Q1, B is equal to C plus Q2, C is equal to Z plus Q3. In A is equal to B plus Q1, delta H2 is equal to minus Q1. And in B is equal to C plus Q2, delta H2 is equal to minus Q2. In C is equal to Z plus Q3, delta Q3 is equal to minus Q3. The total evolution of heat Q1 plus Q2 plus Q3 is equal to Q2. According to Hess's law, Q1 is equal to Q2. If it is not so, let Q2 greater than Q1. Then by transforming A to Z through stages and transforming directly back to A, there would be a gain of heat energy is equal to Q2 minus Q1. By repeating the process again and again, unlimited heat energy will be developed in an isolated system. This goes against the first law of thermodynamics, hence Q1 must be equal to Q2. Application of Hess's law. Calculation of enthalpy of reaction. With the help of Hess's law, it is possible to calculate enthalpies of many reactions which cannot be determined experimentally. For example, it is extremely difficult to measure the heat evolved when carbon burns in oxygen to form carbon monoxide. From the Hess law, it is known that the heat evolved in the combustion of 1 mole carbon dioxide is same vice versa whether the reaction takes place in single step as C plus O2 CO2. Delta H is equal to minus 94.05. When delta H is positive, meaning thereby the enthalpy or heat content of the product is more than of the reactant, an equivalent heat is absorbed by the system from the surrounding. Such reactions which are accompanied by absorption of heat are called endothermic reaction. Enthalpy diagram for an exothermic and endothermic reaction. Thus, for an endothermic reaction, H P greater than HR and delta H is equal to positive, and for exothermic reaction delta P lesser than delta R and delta P is equal to negative. In chemistry, it is customary to represent thermochemical changes as for exothermic reaction HCl plus NaOH is equal to NaCl plus H2O plus 13700 calorie. For endothermic reaction N2 plus O2 is equal to 2NO minus 42,000 calorie. That is, in the case of heat evolution, the quantity of heat evolved is written. The quantity of heat evolved is written with the product with a positive sign. In heat absorption, the quantity of heat is written with the products with a negative sign. In thermochemistry, the attention is concentrated on the system. In exothermic changes, heat content or energy content of the system would diminish, and in endothermic changes, there would increase. Hence, we write HCl plus NaOH is equal to NaCl plus H2O. In this, delta H is equal to minus 13700 calorie and 2 plus O2 is equal to 2NO. Delta H is equal to positive 42,000 calorie. By convention, delta H note T values for elements in their standard state are taken as 0. This aspect has been shown in the following example. Example is given. Heat of combustion. Heat of combustion of a substance is changed in enthalpy when 1 mole of substance is completely burnt in excess of oxygen. Heat of combustion is denoted by delta Hc. The combustion of methane shown as CH4 plus 2O2 is equal to CO2 plus H2O. Delta Hc is equal to minus 87.78 kilojoule. Combustion of hydrogen similarly can be represented as H2 plus half O2 is equal to H2O. Delta Hc is equal to minus 285.29 kilojoule. Now let us consider the following chemical equation. C plus half O2 CO delta H is equal to minus 26 kilocalorie. C plus O2 CO2 delta H is equal to minus 94.3 kilocalorie. It may be noted that minus 94.3 kilocalorie is the heat of combustion of carbon, as combustion is complete in equation B. In the first case A, carbon has been converted into carbon monoxide and by no means completely oxidized. It can be further oxidized to carbon dioxide. Uses of heat of combustion. Calculation of heat of formation. The heat of combustion of organic compounds can be easily determined. These are employed to calculate their heat of formation, or in two steps, as C plus half O2 is equal to CO, delta H is equal to X kilocalorie. CO plus half O2 is equal to CO2, delta H is equal to Y kilocalorie. Although X is the heat change involved in the combustion of carbon monoxide cannot be determined easily, Y is the heat change involved in the combustion of carbon monoxide to give carbon dioxide can be measured and has been found to be minus 67.71 kilocalorie according to Hess's law. According to Hess law, X plus Y is equal to minus 94.05 kilocalorie, or X is equal to minus 94.05 minus 67.71 is equal to minus 26.34 kilocalorie. Thus, delta H heat of combustion of carbon to give carbon monoxide is minus 26.34 kilocalorie. Determination of enthalpy changes of slow reactions. Hess's law is extremely useful in determining enthalpy changes of those reactions which takes place extremely slowly. For example, the transformation of rhombic sulfur into monoclinic sulfur is so slow that direct measurement of enthalpy change is not possible, but the enthalpy of combustion of rhombic sulfur are known to be respectively. First, S rhombic plus O2 is equal to SO2. In this, delta H is equal to minus 297.5 kilojoule as monoclinic plus O2 SO2. In this, delta H is equal to minus 300.0 kilojoule. Subtracting equation 1 from equation 2 and rearranging, then we get S monoclinic into S rhombic is equal to, in this, delta H is equal to minus 2.5 kilojoule, or S rhombic S monoclinic. In this, delta H is equal to 2.5 kilojoule. Thus, the transformation of 1 mole of rhombic sulfur into monoclinic sulfur is accompanied by absorption of kilocalorie of heat. Calculation of enthalpy of formation. The enthalpy of formation of compounds can be calculated by the application of Hess's law when it is not possible to determine these experimentally. For example, it is impossible to determine experimentally the enthalpy of formation of benzene from its elements carbon and hydrogen. However, it can calculate from the enthalpy of combustion of benzene and the enthalpy of formation of water and carbon dioxide, and the solution is carried out in two steps. Adding equation 4th and 6th and subtracting from equation 5, we have C plus 2H2 is equal to CH4. In this, delta H is equal to minus 1660.7 kilojoule. It follows from above that minus 1660.7 kilojoule of energy is required to break 4 moles of CH bonds in methane. Therefore, the average bond energy per mole of CH bond is 1660.7 upon 4 is equal to 415.2 kilojoule. This is also the enthalpy of formation of the CH bond. Summary. In this unit, we have studied different definitions associated with thermochemistry. As we know, thermochemistry is the study of energy changes involved in chemical reaction. This study is very useful in determining enthalpy changes in various reactions. Kirchhoff's equation is very useful in calculating changes of enthalpy with temperature. Hess's law and bond energy calculation are utilized for various transformations. Bond energies. Bond energy for any particular type of bond in a compound may be defined as the average amount of energy required to dissociate 1 mole Avogadro number of bonds of that type present in the compound. This is also called the enthalpy of formation of the bond. Thus, the bond energy of HS bond is the energy required to break all the bonds in 1 mole of the gas. It is expressed in kilocalorie per mole or kilojoule per mole. For example, bond energy of HS bond is 433 kilojoule per mole or 103.58 kilocalorie per mole. Bond energy of some common bonds are given below. Suppose we have to determine the enthalpy of formation of CH bond in methane. We should know the enthalpy of formation of methane. This had been calculated from the enthalpy of combustion of methane to be minus 74.9 kilojoule. Thus, C plus 2H2 is equal to CH4. In this, delta H is equal to minus 74.9 kilojoule. Example, the enthalpy of combustion of glucose is minus 2816 kilojoule. Heat of formation of CO2 and H2O are minus 393.5 kilojoule per mole and minus 285.9 kilojoule per mole respectively. Calculate the heat of formation of glucose. Answer is given here. Calorific value of food and fuels. The amount of heat produced when 1 gram of substance is completely burnt is known as calorific value of food or fuel efficiency. It is expressed in calorie per gram or kilocalorie per gram or kilojoule per gram. Methane has better fuel efficiency than ethane as it produces more heat per gram. It can be explained by comparing heat of combustion of methane and ethane. Heat of combustion of methane is minus 890.3 kilojoule and that of ethane is minus 1559.7 kilojoule. CH4 plus 2O2 is equal to CO2 plus 3HO2. In this, delta H is equal to minus 890.3 kilojoule. And C2H6 plus 3 by 2O2 is equal to 2CO2 plus 3H2O. In this, delta H is equal to minus 1559.7 kilojoule. Molecular weight of methane is 16 and that of ethane is 30. Thus, methane has better fuel efficiency than ethane as it produces more heat per gram. Deciding constitution. Heat of combustion of organic compounds is to a large extent an additive property as shown by the fact that in a homologous series the difference between the heats of combustion of successive members is nearly constant and it's equal to 158 calories. Constants corresponding to the heats of combustions of various atoms and linkage have been worked out. The heat of combustion of an organic substance can be calculated from its probable structural formula by adding up the values of the constants corresponding to the atoms and linkage involved therein. If the value so obtained comes out to be the same as the experimental value of the heat of combustion of the compound, the assumed formula must be corrected. Heat of solution. When a substance is dissolved in a solvent, heat changes are usually observed when reaction takes place in solution. Heat of solution of reactants and products must be taken into account. The heat of solution is defined as the change in enthalpy when 1 mole of substance dissolved in a specific quantity of solvent at a given temperature. If a substance is dissolved in a solvent, certain amount of heat is evolved or absorbed. If the solution is further diluted, there will again be change in enthalpy. If we go on diluting the solution, a stage will come where further dilution produces no thermal effect. This is called the state of infinite dilution. To avoid the quantity of the solvent, we have to incorporate the idea of infinite dilution in the definition, which may be stated as the heat of solution is the change in enthalpy when 1 mole of substance is dissolved in a solvent so that further dilution does not give any change in enthalpy. Thus, KCl plus H2O is equal to KCl. In this, delta H is equal to minus 4.4 kilocalorie. MgSO4 plus H2O is equal to MgSO4. In this, delta H is equal to minus 20.28 kilocalorie. The heat of solution of an electrolyte may be due to energy change involved during ionization or some hydrate formation, as in sulfuric acid. Usually heat is absorbed when ions are torn apart from each other in the process of solution, and heat is evolved during hydrate formation. Thank you.